Okay, it's on. Okay, so in the next few lecture, I'm going to talk about multivariate normal distribution. Okay, so essentially the idea and all the concepts stay the same. It's just that we are moving to a multivariate case. So for example, instead of a scalar y, now we have a vector random variable. So here, this vector of y is denoted as the vector of individual scalar. So this is a n by 1 vector. Okay, so there are n rows and then 1 column, so you can write it as n by 1. And then you can also write it in a real number, but there are n elements there. Okay, so the underlying all the things, the statistical concepts stay the same, except that we are moving in high dimension in this topic here. Okay, so we can also write the random vector y following a normal distribution. And here I'm also going to use a subscript n to denote the dimension for the random variable from this distribution. Okay, so sometimes I will write this n or sometimes not, but this is just referring to a dimension for this random variable y here. Okay, and the normal distribution also come with two parameters. Okay, so now let me first write it down, and this is the mean vector. So the mean vector, let me put it, maybe I'll put it in here. Okay, so my mean vector is referring also a n by 1 vector, and then for each of the elements is mu1 all the way to mu n. So this is a column vector with n elements, so it's a mean vector. Okay, and then for the covariance, now it's a matrix. So let me put this is n by 1, this is also n by 1, and then for the covariance matrix is n by n. And this one is, if you do it on latex, it's the capital sigma, as capital S sigma. So this is the sigma referring to the matrix. You will usually see the similar symbol for the summation, but in latex it's different, and then it looks the same, but this is referring to the sigma matrix. So in latex you type capital S sigma. Okay, and this n by n matrix consists of the following n by n elements. Okay, so first of all, it's an n by n matrix, and let's fill out the diagonal elements. So on the diagonal, so here is 1, 1 entry. We have the sigma, lowercase sigma 1 square. And then for the 2, 2 entry, you have the lowercase sigma 2, subscript 2, and then square, all the way to the sigma n for the nth elements, and then sigma square. Okay, so that's the diagonal elements. And now let's talk about the off-diagonal element to be a symmetric matrix. So that means for your 1, 2 entry, you will have a sigma 1, 2. So this is referring to the first row, second column. So you have a 1, 2. And then since this is a symmetric matrix, for the 2, 1 entry, so which is this elements here, you can write row 2 and column 1. Okay, and also there's no more square here. Okay, so this is the 2, 1 entry and the 1, 2 entry. And because this is a symmetric matrix, so you have sigma 1, 2 equal to sigma 2, 1. And then for all of the I not equal to j, you will have sigma, okay, so let me put it down. You will have sigma ij is equal to sigma ji for all, or let's say for j, for I not equal to j. Well, if you want, when I equal to j, it just itself, like scale, like sigma 1 square is just sigma 1 square. Yeah. So if you want, you can just do it that, like for I not equal to j. And then they are symmetric. Okay. And then similarly, all the way, you will have the row, the first row, and then the nth column, and then you will have the nth row and then the first column, and then you can fill out the remaining matrix here. Okay. So that is your n by n sigma matrix or covariance matrix. Okay, so similar, just to make an analogy to the univariate case, you have the scalar variable with n, mu, and the sigma square. So here, these are all scalar. Okay, so in R, or R positive. But here we are doing the R with the n by 1, or Rn, and then Rn by n. Okay, so that is the only difference. And then sometimes, okay, and here the covariance, so for any elements that is not on the diagonal, they are sometimes called the covariance between the ith and jth coordinate, and sometimes you will see people doing some reparameterization as like ij, sigma ij is equal to rho with the standard deviation for that I and then sigma for the j. Okay, and then you will get the covariance of the, so this is more like a covariance, and then this is the standard deviation for each of them, and then you will have the correlation. There's one. Okay, so just a common for now. Okay, then let me put it down for now. Okay. Okay, but we are not going to work on this, so yeah, this is more just a side note. Okay, for now. Okay, any question regarding our notation? It's just the same normal distribution, but we are moving in high dimension for now, with n dimension particular. Okay, so that is the, I don't want to keep this one here, so let's move it out, but that is just a side comment. Okay, so now let me introduce the probability density function for this multivariate case. So we will have the PDF. Okay. I usually erase lots of things that I find very ugly in the screen, so I like to keep it neat. So yeah, okay. So the PDF. So let's again denote it as f of y. Okay, so that's your random variable, which is a vector. Okay, so similarly, so you will see how it resembles the univariate case. So here is the multivariate case. So you will have 2 pi. That's something that in the normalizing constant. And then here, you have to raise to the power of negative n over 2. And n is for the dimension for your random variable y. Okay. So you also see a 2 pi, 2 multiplied by pi in the denominator in the univariate case. And the next term here is called the determinant of the sigma or the covariance matrix. Okay, so you have the determinant. So sigma is the n by n matrix. The determinant will return a scalar. Okay, and for this one, you need to raise the power of negative 1 over 2. So it's a scalar raised to the power of 1 over 2. And just in case if you're not familiar with the negative or the 1/2, so for a, let's say a scalar a, if you raise to the power of negative 1/2, this is, first of all, let's work on the 1/2. So this is saying you have a taking the square root, and then you still have the negative 1/2. And then the 1/2 is just saying this is in the denominator. Okay, so you have 1 over square root of a. So you can imagine that this is the 2 pi raised to the power of n, but you square root of that and then put it in the denominator. Okay, so that is the negative 1/2. So negative is pushing to the denominator. 1/2 is just taking a square root for a scalar. Okay, so this is also a scalar. So 2 multiplied by pi, and then negative is in the denominator, and then you raise to the power of n, but taking a square root. Yeah. Okay, so sigma matrix, you get a determinant negative 1/2. Next is for the rest of the term in the exponential. You will have the exponential. So let me use a square bracket. And then you also have a negative 1/2, also in the similar in the scalar case. So now we are going to apply the matrix vector multiplication or operation. So here you have the column y minus a column vector of mu. Okay, so that will still reduce to a column vector with n entries. Okay, and then here you will have a transpose operation. Are you guys familiar with the transpose or? Okay, good. And then you will have the sigma matrix. So let me first finish the formulation and then I will talk about that. And then you will have the y minus a mu, completing the formula, and then closing it with the square bracket. Okay, so each of the term are scalar, okay? So this will return a density for your, for a particular, let's say, realization if you plug in. Okay, so each of them is a scalar. Okay, so now let me just comment a little bit on the matrix vector multiplication. So I think, okay, yeah. So here, let me first introduce the transpose operation. So again, you have the variable y, which is y1, y2, all the way to yn, a column vector with n entries. Okay, that is a, so usually so if you're reading some paper or without other specifications, sometimes people use column vector if they don't say anything, they really refer to column vector. And then when they do a transpose, it's essentially just flipping in a different, like a, how do you say that, direction, if you want to put it. So if you do the y transpose, you still have y1, y2, it just, everything become horizontal. So that is the only difference. So that is the transpose operation, okay? So transpose is mainly for vector or for matrix. So here you have the column vector, when you do transpose, become a row vector. Okay. Okay, so that is for the vector. Now let's do a matrix. So let's do a square matrix, or maybe let's do a non-square matrix. Okay, so let's do A1, A2, and A3. A4, A5, and A6. So this is a 2 by 3, so 2 row and 3 columns matrix. That is that. Okay, and then the matrix A transpose, it just flip on the diagonal. That diagonal, what do you call that? You call it reference line, that kind of things. Okay, so you will have A1 here, and then A4 on the row, okay, and then you will have A2 and A5, and then A3 and then A6. So you are essentially flipping on, like, if you call this the reference line, so you are essentially flipping on that normal line or reference line, and then you're flipping in that way. So you started with a 2 by 3 matrix. After the transpose, you will end up with a 3 by 2. Okay, so that is the more of a definition for the transpose of a matrix. Okay. And then for a square matrix, so let's say when you have a n by n matrix, and if this n by n matrix is equal to A transpose, we call A is a symmetric matrix. Okay, and that is the case for our sigma matrix in this normal distribution. So here we have that they are. So if you flip along the diagonal, this direction, if you flip the matrix, you will still get itself. So our sigma matrix, the covariance matrix in a normal distribution, is a symmetric matrix. Okay, and then here let me just comment on the dimension. So you will have a n by 1 minus a n by 1 multiplied by n. So before that, this is a n by n, and then here you also have a n by 1 and then n by 1. Okay. So when you perform addition, subtraction, multiplications, you need to make sure that their dimensions are aligning. So here, when you have n by 1 minus n by 1, that's a valid operation. It will ends up with a n by 1 matrix. Okay, n by 1 vector. And then here you have an n by 1, but the next term here is a n by n matrix. Okay, so if you do n by 1 multiplied by n by n, that is not a valid operation. But here, people introducing a transpose operation, so that means you will have a 1 by n, and then n by n, and then multiply by n by 1. So this 1 by n is coming from the transpose of n by 1. Okay, once the dimensions are matching, this will be a valid operation, and in the end, you will have a scalar as the output. So this one with this one as your final dimension of the output. So you have a 1 by 1 matrix or 1 by 1 scalar. Okay. So first of all is that for matrix vector multiplication, you need to make sure the dimension is matching to perform the operation. Okay. Any question or comments regarding notation and the PDF for the multivariate normal? Okay. Now let's talk about some. Okay, before that, we also have a special case as in the univariate. We have the standard normal. So now let's call this a z, which is also a column vector. And then we will have a normal distribution dimension of n. And this is referring to the mean with a 0 mean vector. So this is a vector of n of zeros. Okay. And then here you have a identity matrix. Let me also denote the subscript n here. And the identity matrix here, so the 0 matrix is referring that you have a vector of zeros. So n zeros. The identity matrix is referring that your main diagonal elements are all 1 and the remainings are all 0. Okay, so I'm just leaving it empty, but the empty part is referring to the 0. So only the main diagonal elements have a entries of 1 at each coordinate, but the remaining entries that I did not write it up, filled up, those are all zeros. Okay. So you essentially have a 0 mean vector identity covariance matrix, and that is referring to the parameter of a standard multivariate normal. Okay. And if you want to think about it in the scalar version, this is just the zi, where I ranging from 1 to n, each of the zi following a normal with 0 and then variance sigma squared equal to 1. Okay. But for the not standardized version, for this one here, you cannot write it in that way. Okay. The reason is that when the off diagonal elements are 0, that means the coordinate wise there's no covariance. So then they are independent. Okay, that's just a special case because these are 0. But if they are not 0, then you cannot simply write it like this, like the scale, like the element-wise, random variable or the element-wise. You have to write it in a vector form. That the vector y follow a multivariate normal with a vector mu and the matrix sigma. Okay, and then just to complete this part, let's write down the density function for your standard normal variables. And then you still have the 2 pi raised to the power negative n over 2. And then the determinant of the sigma matrix for a, what do you call that? I mean, more general, what do you call it? Diagonal matrix? Yeah, I think, yeah. For diagonal matrix it just means they're all zeros on the other element. So for the determinant, it's just the product of the main diagonal. So in our case, they're just all 1, right? And then for 1, you still have to raise to the power of the negative 1/2, but it's still just 1. So that the sigma matrix just it's 1, or you can think it as it disappears. Okay, but essentially the determinant of the identity or a diagonal matrix is just the product of the diagonal, and then it's just still going to be 1, so it disappears. And then you still have the exponential part, negative 1/2. And then you have the z minus the mu, but the mu is 0, so you have the z itself. And then for covariance matrix is the identity, so anything multiplied by identity is still itself, so the covariance matrix still disappears. And then you have the other half for the z minus the mu. The mu is 0 again, so you will have this as your density. And then you can also remove this 1, but it's just itself. Okay, so that is the PDF for a multivariate standard normal distribution. Okay, so before we proceed some other statistical topics, any question regarding the just like the formulation right now? Any question or comments?
Can you repeat the significance of the zi independently distributed?
Sure. Here it's just that, for example, your covariance between z1 and z2. So this is for the, okay, so z1 and z2, the covariance is 0. So that is saying z1 and z2 are independent. So you can consider that z1, z2, they are independent. And then also in this case, identically distributed. Okay, yeah. There are lots of variations. So instead of the diagonal of 1, you can also have sigma 1 square, sigma 2 square, all the way to sigma n square, and the remaining entry as 0. Then your zi's are independent but not identically distributed in this case. So here they are all same covariance. Then you have independent and identically distributed for the element wise. But for this case, they are independent but not identically distributed because the covariance are different. Okay, and then some other special case will be, so I'm just not going to say more, but there are lots of special cases. I don't want to confuse you, but here are just the 2 major ones we will work with. Yeah, because the covariance are 0, they are independent. Yeah, and in this case, they are also identically distributed. IID. So, yeah. Okay, next, let's talk about moment-generating function for multivariate case. So I'm going to call this joint multi-MGF. Okay, so first of all, let's introduce a vector of t. So this is the, so again, in the scalar case, I always emphasize that moment-generating function is a function of t. So here again, the joint moment-generating function is also a function of t, except that the t here is a scalar, it's a vector. Okay, so t1, t2, all the way to tn. So it should match with your dimension of the random variables. Okay, so let me use a generic letters here. I'll just use x, and then you will have the same x1 all the way to xn. Okay, so now I'm referring, x is my random variable or random vector, and t is the input of that function for the moment-generating function. Okay, so similarly, we will have the same definition, for the moment-generating function. I'm going to use letter m for the function name, and then a subscript x. So here, the only difference is that the subscript x is a vector, and then you will also have a vector t. So same notation, m of t with a subscript x for the random variable that you are working on, okay? Let me call this the definition for now. And this is the expectation of e. So this is the exponential term, exponentiated. And then you have the vector t transpose x, okay? So when you have the scalar version, you just have t multiplied by a scalar x. For the vector operations, you have the vector t transpose x. Sometimes this is called the inner product as well. Okay. So this is the, let me put it here. This is the vector version, and you have the scalar version. So expectation e just raised to the power of tx, where t and x are both scalar. So this is your scalar version. Okay, so the only thing is that you need to do an inner product of the two vectors to get a scalar, and then you put it in the, you exponentiate it, and then you will get a scalar. Okay, so it's more like a notational difference, scalar version, like vector version. Any question, comments? Yeah. Let me comment a little bit on the inner product. Okay, so here you have the t vector of 1 to n, x vector of x1 to xn. The inner product, so vector of t transpose x, is referring to the t vector. First take the transpose, so t1 to tn, and then multiply by x1 to x2 all the way to xn. Okay, and then if you want to do more with like a element wise and then also involving index, then you can do it summation I from 1 to n. So this is the summation instead of not the sigma anymore. So if you want to do it the index way, you can do summation I from 1 to n, and then ti multiplied by xi, where ti and xi are the corresponding elements in that vector. So it's a scalar ti, scalar xi, take the product, sum them together. And that is what the inner product is defined. Let me put it here. Inner product. Or sometimes people call it dot product. What are some other names? Inner product, dot product. Any other names? So yeah, usually that is just what people are referring to, the t transpose x for the vector. Yeah. And then you will end up with the scalar. So here is vector of vectors, multiplied by vector, you will end up with scalar. Okay, any question, comments? Now let's derive the homogeneous function for the multivariate standard normal. Okay, so let's use the definition. So homogeneous function for vector z, vector t. Your definition is the expectation for e raised to the power of the vector t transpose random variable, random vector z. Okay. And then I'm going to write it expectation e raised to the power of t1 multiplied by z1 plus t2 multiplied by z2 plus all the way to tn multiplied by zn. Okay, so that is just the definition of the inner product that I put it over there. Okay, the summation for I from 1 to n, that thing, I just write it out explicitly. Okay. One thing that was just common is that the standard what do you usually call the order? Standard multivariate standard normal. Okay, one thing that we just mentioned that is that they are independent element-wise. Okay, so I'm going to, for this equal sign, okay, so here let me put, this is the definition, and then for this equal sign let me put independent. Okay, so that's the thing that we just noticed. Because they are independent, and then coming from the product, this is one of the property in the scalar version. You have the expected T1, Z1. So now they are all scalar. And then expected Z of T2, Z2. Okay. So now we reduce from vector to scalar version. T2, Z2. All the way to expectation E of Tn, Zn. So up to the first line is still vector operation or vector notation. The second line here we're reduced to the scalar version. Okay, and this is due to the independency there. Okay, and can someone still or anyone still remember what is the moment generating function for the scalar version, the standard normal variables? E raised to the power of negative. Okay, so let me write it. Yeah, so 1/2 t squared. Is that what you mean? Yeah. Okay. So I'll put the 1/2 in the front. Yeah. Thanks. Yeah. So. Yeah. Okay. So this is the moment generating function. Moment generating function for the scalar version. So this is saying z following a normal, scalar 0, scalar 1. Okay, so now we know that each of the elements you have a moment generating function in this form. So let's continue the equation, the equal sign here. So that means you will have the e raised to the power of negative 1/2 and then t1 squared multiplying e raised to the power of negative 1/2 and then t2 squared all the way e negative 1/2 tn squared. Okay, so here from this line to this line, I'm just borrowing the scalar version of the moment generating function. And then the product of the exponential is the exponential of sum. So I'm going to write it exponential. So now I'm going to write the exponential negative 1/2. Let me still use the e notation then. Okay, so e raised to the power of negative 1/2 and then t1 squared plus t2 squared plus all the way to tn squared. Okay. Any question up to this point? So the product of exponential is the exponential of sum. So I'm just summing all the powers here. And then I bring the negative 1/2 out, you will have the summation from 1 to n squared. Yeah. Okay, now let's write it in the compact form. Let's do the opposite of the inner product. You have the e raised to the power of negative 1/2 t transpose t. Okay, so t transpose t is the inner product is just the element-wise sum and then element-wise product and then take the sum. So now I'm doing the opposite way. I'm writing all the sum into inner product. So just to make it compact notation. Okay. So vector matrix multiplication, they operate the same as the scalar version. It just you write it compactly. That's the main difference. So you can see that when you have lots of summation, that's a vector multiplication. Okay, so just to remind you, this is the MGF for Z that follow a multivariate n dimension, 0 and identity matrix. Any question regarding the moment general function for the multivariate standard normal or standard multivariate normals? Okay, if not, let's do the general normal version. So in scalar, in the scalar version, when you have z follow a normal 0 and 1, when you do how do I write it? Maybe I write it here. Okay, so when you do y equal to mu plus standard deviation z. This is saying, so after this transformation, you will get y following a normal with mean mu and the variance sigma square. So here is the standard deviation, here is the variance, okay? So this is the transformation that we mentioned in the scalar version. Okay, similarly, we can do it in the matrix vector version, okay? Again, you have the z following a normal n dimension 0 identity. So now the transformation y is referring to the mean vector. It's a vector plus your covariance matrix but raised to the power of 1 over 2. So this is the matrix raised to the power of 1 over 2 and then multiply by z. Okay, so if you have a transformation that look like this, then the resulting random variable y is following a multivariate normal with mean vector mu and then covariance matrix sigma. So this is sigma 1/2, this is sigma matrix itself. Okay, so this is just a scalar and the vector version, but essentially they are the same thing. Okay, so once we introduce this transformation, let's work on the moment general function for the general normal, where y is following this mu and sigma matrix, vector of t. Okay, so now let's replace the y with this transformation. We have mu plus sigma 1/2 multiplied by z, vector of t. Okay, so now let's put it in the definition for the moment general function. So in this equal sign, I'm going to put definition. And then we have the expectation, e, raised to the power of all those things. So you will have, okay, so then let me do it step by step, just in case if you are new to the matrix vector forms. Okay, so let's go back to the definition. You have the t multiplied by the random variable. Okay, so in this case, you will have the t vector transpose multiplying by mu plus sigma 1/2 multiplied by vector of z, and then that's that. Okay, so I'm just doing the definition by plugging whatever in the subscript onto the power. Okay, next, let's distribute the t into the sum here. Expectation, e, and then you will have the t transpose multiplied by mu plus t transpose, and then sigma 1/2, and then multiplied by z. Okay, so you can see that the product and sum when you're distributing the terms, it operates as in the scalar. So a multiplied by b plus c is equal to ab plus ac. That's the thing. Okay, so let me ask a quick question. What is the dimension of t transpose mu? A scalar, right? What is the dimension of T transpose sigma 1/2 Z? Yeah.
Is it 1 by n?
You mean the result?
Oh, I'm talking about like the T transpose and the summation 1/2
Sigma.
sigma
Yeah.
1/2.
Still 1 by 1.
Yeah. So you were saying this part is 1 by n, and then this is n by n, right? Yeah. And then you have the n by 1. So you were saying this part, right?
Yeah.
This is
that
1 by
was-
n.
that was just that part.
1 by n. Yeah. And then after you have the n by 1, you answer with a scalar 1 by 1. Yeah. So here I just want to say that the result is still going to be a scalar. Yeah. So here you have 1 by n multiplied by n by n, and then multiplied by n by 1. And then you have n 1 by 1 in the end. And then everything is still a scalar. It's a output of a function, right? It's a function, homogeneous function. Function outputs a scalar. Yeah. Although the things inside can be high dimension, the output is scalar. Okay. Let me ask a follow-up question. What is random variable? What is not random variable in the things inside the parenthesis?
C is a random variable in mathematics.
Okay. So we have the random variable z, so the rest are just a constant, and then we can apply lots of property. So this is and also this is scalar, so we can apply lots of the properties of the homogeneous function that we introduce. Okay. So first of all, this part is okay. I'm not sure how much. Okay. So the first part is a scalar, it's a constant, so I can bring it outside. Hmm?
Yes.
Yes.
What? Huh?
We're just excited about that.
Oh, okay, okay. Okay. T transpose sigma 1/2 and then z. Okay. The reason I'm bringing, okay, so first of all, exponential of a sum is the product of two exponential. So you have the e of t transpose mu multiplied by e of t transpose sigma z. That's the product. And the first part that I refer is a constant, so you can move it outside the expectation. Okay? So as long as the random variable is still inside the parenthesis, then you are good. So I move the constant outside. So the thing that I underline here, this is a constant. So I move it outside the expectation. Okay. Any question up to this point? Okay. So what I'm doing here, just I move whatever I identify as a constant, I move it outside. That is what I'm doing. Okay. Next, let's work on whatever is inside the expectation. Because it involving random variable, so we need to work on that part. So first of all, so this is also the trick that I often use, and also I mentioned that it's a good, okay, so because this is the first time I talk about this, so maybe let me be more a little bit precise. So first of all, so for this line, it's very a small change. I'm just changing the notation. So I'm writing the sigma 1/2 and then multiply by t. I group these two together, transpose z. Okay, so the only difference from this line to this line is just I group the sigma and the t together. Okay, so I mean, I will just do it for this time, but in the future, I'll just assuming that it's very obvious to you, so and then I will just not doing this step. Okay, so what I'm doing here is that you have t transpose sigma 1/2 and then z. This is, so after transpose, this is 1 by n, n by n, n by 1. Okay, so you should get a scalar. What I'm doing is that I group these two together. I group sigma 1/2 multiplied by t. I group these two together, transpose multiplied by z. So now if you look at that, here you have a n by n. You have a n by 1. So the things inside the parenthesis is a n by 1. After you take a transpose, you will have 1 by n. Okay? And then here you multiply by 1 by n, you have a scalar. Okay? So when you group the thing, so here is product of A, B, C. I'm grouping A, B together multiplied by C. The same idea works, but when you do the transpose, the order here matters. Okay. So this is saying okay, so I'll just mention this time, but next time I'll just assume that it will be obvious. And then, okay, so what I'm doing is that a matrix A multiplied by matrix B, and then I'm taking a transpose. In the matrix operations, when you do a transpose of a product of the matrix, this is equal to B transpose multiplied by A transpose, okay? And this is not equal to A transpose and B transpose, okay? So transpose of AB is B transpose, A transpose. So the order here matters, okay? And the other order is not the same, okay? So that is what I'm doing here. And then another thing that I imply here is that sigma 1/2 transpose is equal to sigma 1/2 because it is symmetric matrix, okay? That is what I'm implying here. Any question regarding some of the operation here? Can I get a show of hand, like if the matrix vector thing is familiar or or if you guys prefer, I talk about some more details regarding the operations. Can I see a show of hand, like if I go over the
I would be happy for more details.
more details? Okay, then I will go through. So if this is right now the details okay for okay? Okay,
Yeah.
good. Yeah. Yeah. Any question or comments regarding matrix vector operations? So, all good or okay? Okay, so I'm just working on this term here, and then I'm grouping T transpose sigma, and then apply using this one here. I group these two together. So A, B, C, I'm grouping A, B multiplied by C. But the thing is that the A, B, you need to write it in the reverse order so that it makes sense here, okay? So you have to write B, A, so that the transpose is A transpose, B transpose, okay? And the B transpose, there's no transpose here because this is symmetric, so there's no more transpose, okay? Okay, so that would be the details here.
So why is
Yes.
that symmetric?
Oh, it just the very underlying reason regarding the symmetric is that this is saying the covariance between random variable z1 and z2. The covariance of z1 and z2 is equal to the covariance z2 and z1.
Gotcha.
So they are symmetric. So this matrix is symmetric. But the interpretable reason is that the covariance are like a symmetric, like z1 is covariance z1 z2 is equal to covariance z2 z1.
Gotcha.
And similarly for all the I not equal to j. Yeah. So the entire matrix is symmetric. That means you can flip according to this. If you flip it just itself. Yeah. So they're all symmetric. That is just like a property for the normal multivariate normal. Yeah. So for all the covariance, it has to be all the covariance matrix. It will all be symmetric and positive semi-definite. But that's something else we'll talk about later. Yeah. Okay, so after I grouping these two, now this is the trick that I often do, and also I have also used in the scalar version. So now I'm going to call T star as sigma 1/2 T. Okay, so essentially just the thing that I grouped together. Let me just call this T star. So that means, so let me just call it define T star as that, just like a naming thing right now. There's no more technical, just I call this the T star. You can group whatever things you want together and then make it a new name, okay? And now let's continue the equal sign. So from here, you will have the e raised to the power T transpose mu, okay? So that is the constant from here, okay? So I'm bringing this constant, which is also a scalar, to the bottom, to the first part. And then the expectation, you will have E. So right now, after grouping the things together, let me call T star transpose, and then what is the other thing? Z, yeah. T star is a new vector multiplied by a vector of Z. So T star is also n by 1, so transpose is 1 by n multiplied by n by 1, you still have a scalar, okay? So what I'm doing here is that I first separate the constant. I bring the constant outside the expectation. Then I group sigma 1/2 and T together. I call them my T star. And then that is just using the T star thing here. Okay, so that is what I've been doing here. So you might ask why we are doing this kind of tricks here. The reason is that because we know the moment-generating function for the multivariate z. Okay, so now I'm going to borrow the moment-generating function for the random variable z. Okay, so let's see what is the one that we derive. Okay, so negative 1/2 T transpose T. Okay, so now I'm going to borrowing the moment-generating function that we derived earlier to here. So you have the e raised to the power of negative 1/2, and then T star transpose T star. So the T star is the T in the moment-generating function. Okay. So here I'm just borrowing using moment-generating function that we derived earlier. Using the MGF of vector z. Okay, so I'm just borrowing, but plug in T as T star as T. Yeah. Next, let's replace the T star with what we called, and then we will have a complete form. Okay. E of T transpose mu, that's the constant part, e of negative 1/2, and then let's bring back what we call the T star. Okay, so T star, so now let's bring it back. We will have T, okay, so let me not jump steps just for the first time when I'm doing this. So T star is sigma 1/2 and T, sigma 1/2 T, yeah. Okay, that's my T star. And then the T star, you have a transpose. And then you have another copy of T star. Okay. And then let's decompose, or let's remove the parenthesis. So transpose of AB is B transpose A transpose. So in this case, you will have sigma 1/2 transpose. But this is symmetric, so it becomes itself. And okay, so you have to do the T first. So B first. So B transpose sigma 1/2. And then you have the sigma 1/2 and then the T. Okay, so again, A, B transpose is B transpose, A transpose. So the order matter, okay? So let me put it here. Order always matters in the matrix vector multiplication. So what I'm doing is that I remove the transpose, I distribute the transpose to the first term. Okay, so what I'm doing is that I call A my sigma 1/2, my B is my T. So then you will have to build T transpose, which is this one here, and then A transpose is just this one. And because they're symmetric, so A transpose is just itself. Okay. Any question up to this point? Yes, yes. That's a very good question. Actually, at this point, it will be very difficult to define. Maybe I will comment a little bit when we really talk about the details for spectral decompositions, and then the 1/2 will make more sense. But right now, let's just think about it as you raising 1/2 power to a matrix for now. But there will be some more implications. That's a very good question, and we will talk more about that. Yeah. I think when we do the spectral decomposition of a matrix, the 1/2 will be I would say easier to visualize, to understand, to think about it. Yeah. But right now you can just think it's like a power to a matrix. Yeah. And then we will talk more about that. Yeah. Thanks for the question. Yeah. Okay. That's a very good question. Yeah. And now, before we start, any question up to this point of the notation or operation? Okay, so one more thing before we, okay, so there is one more thing regarding this 1/2 I want to talk about, is that the sigma 1/2 multiplied by sigma 1/2 is just equal to sigma matrix. Okay, so this is a n by n, this is a n by n, this is also a n by n matrix. Okay, so you can think of this as the scalar version. So a square root multiplied by a square root, this is equal to a. Square root is just -1, power of 1/2. Okay, so similarly, so this is the matrix, the matrix version, the scalar version. So a raised to the power of 1/2 multiplied by a raised to the power of 1/2, it just weigh a raised to the power of 1. It's just scalar, or a itself. Okay. So back to our equation. You will have E T transpose mu. So these are two vector, and then E -1/2 T transpose. So I'm grouping these two together. Okay. So when they are multiplying together, you will just have the sigma matrix. Okay. I'm applying this rule here. Sigma 1/2 multiplied by sigma 1/2 equal to the sigma matrix. Okay. And equivalently is just the scalar version thing. Okay. But in this case also work on the matrix. Multiplying by T. Okay. So now I'm going to group the two product together. E of let me group these two together. T transpose mu plus 1/2. Where did I? Okay, there's a typo. I carry on. Okay, can someone take a look at the previous notes for the homogeneous function of normal? Is there a negative sign or not? Okay, I got.
Yeah.
No, okay, I need to double check myself. Okay, here. Where did I introduce normal, standard normal?
Oh, the homogeneous function?
Yes,
Oh,
and
there is
G.
no
Did you tell me there's a negative?
Yeah, sorry.
Okay,
I already did the PDF.
okay. Okay. So no, I think I also made the mistake. Okay. Okay. Sorry about that. I carry on. I was just using. Okay. So the thing is that there's no negative sign in the homogeneous function of normal. Okay. So all the things here, there's no negative. Okay. Sorry about that. Sorry. Okay. So in the scalar version, there's no negative sign. I was wondering why. Yeah, there's no negative. If you, yeah. When did I talk about the homogeneous function for the scalar version? It's okay. Never mind. So the thing is just there's no negative sign. Okay. So there's T transpose sigma T. Okay, so let me emphasize again. So when we're deriving the homogeneous function here, we are borrowing the information from like previously in the scalar version. And then there's no negative sign here. Okay. Yeah. So then we take the product, there's also no negative sign here. That is the, so again, the multivariate case, there's also no negative sign. Okay. And then here, there's also no negative sign. And in the end, that means this is a plus. Do you guys, we'll come back in 5 minutes. Sorry? Yeah, can you speak up? Can you speak up? No.
Do you mind scrolling up a little bit before we started generating function for the
Today's lecture. Okay. Which part? Keep going up.
like right there.
This one? Yeah.
Chicken noodle soup, lemon, lentils, roasted Brussels sprouts. Roasted Brussels sprouts.
What is it? Well, it's an exact same one.
Yeah, I didn't like chickpeas. So I like roasted asparagus and
leading to file.
I think it's hard for some
And that's
What did you say? We know that from calculating distance between every single swap before the current one. Yeah. Honestly, this doesn't every time I like feel like I'm trying to incorporate ChatGPT functions, I just like make shit up. Like what I'm talking about, I was like just go back to where it was. I could fall asleep from like yeah. Oh yeah.
This was like start of last week's It's the basis of
Okay, so let's continue. In week 3 and lecture. In week 3 and lecture 4, here is where we derive the actual homogeneous function. So you can see that there's no negative sign. So it's e raised to the power of negative e raised to the 1/2 t squared. So there's no negative sign here. Okay. So in week 3 we derive it, and then that's the homogeneous function, and that is the thing that I borrowed today. So we use it the 1/2 t squared. Okay. So again, week 3 and lecture 4. Okay. So there's no negative sign here, and then I'm borrowing this term that we derive on week 3 to this part here, to this part, okay? So there's no negative sign, I'm using that term, and then when you multiply them together, you will have that, and then there's no negative sign here as well. So as you have seen that in the scalar version, this is 1/2 t squared, and then in the vector version, this is 1/2 t transpose t. And then I'm borrowing that again in the general case. So I'm borrowing to here. So t star transpose t star. So again, there's no negative sign here. And then all the logic follows. And then here is the moment Jenny function for the multivariate normal. In the scalar version, you will have the e raised to the power of mu t plus 1/2 sigma squared t squared. Okay, so this should be also coming from week 3, lecture 4. So this is the scalar version. Okay, let me write it more. Let me just use x then. X of t. This is the scalar version. This is the, let me put it here, vector version. Okay, so you can see that it's very similar, except that we are just using transpose or matrix operation. So mu t, and then in vector t transpose mu transpose. So again, order matters here. For the scalar version, order doesn't matter. T mu and mu t is the same thing. So ab multiplied by ba is the same. Vector, you have to measure dimensions. 1 by n multiplied by n by 1, you have a scalar 1 by 1. And here, 1/2 t squared. So t squared is this 2t, sigma squared, sigma. So the order mattered there. Okay, but you can see the formulation is similar. And again, there's no negative sign here, so there's also no negative sign here. This is a plus. Any question or comments? Okay, what else do we have for today? Okay, since we're talking about moment-generating function, now let's talk about general joint moment-generating function, not necessarily to be normal. Okay, joint MG. Okay, so let's consider a random variable. There are only 3 entries, x1, x2, and x3. And I think this is also related to your homework problem. I just posted online. And yeah. So here, the moment generating function for x and t, and you can also write it as m of x1, x2, and x3. This is saying this is a multivariate random variable. Okay, so it consists of 3 variables, x1, x2, and x3. Okay, then correspondingly you have t1, t2, and t3. If you don't, so here I'm just writing element wise. So in a subscript you have x1, x2, x3. In the parentheses you have t1, t2, t3. Okay, and then you will have a function on the right hand side. So some formulation of the moment generating function. Okay, so now one properties regarding these moment generating function or the multivariate case is that if you want to get the moment generating function for x1, t1, this is equal to the moment generating function for the multivariate case t1, but setting t2 equal to 3, t3 equal to t2 equal to 0, t3 equal to 0, you will get the marginal moment generating function for that single random variable. Okay, so let me repeat. So when you have a moment generating function for a multivariate random variables, and then if you are interested in the moment generating function for a particular random variable, so let's say x1, all you need to do is just set the t's corresponding to the other elements to 0 and leave the t1 inside your formulation. Whatever you get on the right hand side, that will be the moment generating function. So that will be your moment generating function for x1. And this is the moment generating function for x1, x2, x3. So to get moment generating function for x1 from moment generating function for x1, x2, x3, all you need to do set t2, t3 to 0. Whatever expression remaining on the right hand side will reduce to the marginal case. Okay, so that is one kind of property that related to homework. Another thing is that if x1, x3, t1, t3, so for this one you can obtain by setting t2 equal to 0 if you have the joint. Okay, and then if this one equal to the marginal x1, t1 multiplied by x3, t3, so if this equal sign holds, this implies x1 is, let me just use word, independent of x3. Okay, so one way to check if your sub-elements in your x1, x2, x3, that vector, if you want to check any of them are independent, you can using this to the equal sign. If they're equal, then so you know how to get this by setting t2 equal to 0. You know how to get this by setting t2, t3 equal to 0. You know how to get this by setting t1 and t2 equal to 0. So if this equation still hold x1, x3 independent, you can make the conclusion there. Okay. Okay, we still have 15 minutes, so I think I can cover the next result 1. Okay, any question up to this point? Okay, then let me cover one more results, and I think that would take yeah. Let me also put it as the examples or results 1. Let Y follow a multivariate normal with mean and then the sigma matrix. Here I'm performing another transformation. Let random variable x equal to a multiplied by y plus c. Okay, so here you can make it as general as possible. So let A be a matrix of m by n. So they don't need to be square. It can be rectangle, that kind of shape. So m not equal to n, okay? And then you have y still equal to n by 1. And that means your c must be n by 1, okay? So we can just make up any dimension. So we have matrix multiplied by y plus a vector of c. So equivalently, you are just scaling your random variable and shifting by c. Scaling by matrix of A, shifting by C. So my question is, what is the distribution for X? Okay, that is my question, and that leads to the result 1. Let me write down. What is this distribution of X? The X is a linear transformation of your random variable Y, where Y following a normal distribution. Okay, so that is what we are going to do next. And any thoughts on how we verify what is the distribution of a new random variable? Some trick that we did before. What are our strategy here?
Can we just look at the energy of it?
Yes, exactly. So to confirm what distribution is, a good tool is always to look at the Montagnier function. Okay, so we are interested in the Montagnier function of the variable x. Okay, and variable x is m by 1, so a vector. So that means t is also a vector. We are doing a joint Montagnier function here. Okay, now let's make the change of variable. This is the ay plus c vector of t. Now let's do the definition. Expectation and using the okay, so now I'm going to use t multiplied by that, and that will give me okay, so now I'm going to okay, so I hope that this is just the same as before, but I'm going to write the result directly. So you have the t transpose multiplied by ay. So I'm distributing this t to ay plus t transpose multiplied by c. Closing the square bracket, closing the parenthesis for expectation. Do you agree with that? Any question, comments? Okay. Expectation, exponential of sum is the product of the exponential. So we have expectation and then exponential of t transpose ay of that multiplying exponential of t transpose c. Okay, so product, the exponential of sum is the product of exponential. What is, so let me ask you a question. What is the random variable? What is constant here?
Y is a random variable, and C and A are constant.
Yeah. Okay, so the second term here is a constant, so let's bring it outside of the expectation. So t transpose c. and then the expectation will still have to, so random variable will still have to fall into the expectation. T transpose A Y, closing that and closing this parenthesis. Okay. Let's see what else. Okay, so now let's do a regrouping thing. So I'm going to group T and the A together, call it T star. Okay, so same trick. And this is still the constant part. And expectation, exponential. So when you group these two together and then you want to group it and you still want the transpose, so you need to change the order. So A multiplied by T transpose multiplied by Y. Okay, so what I'm doing is that I'm grouping A and T together and then leaving Y as a single term. And the reason is that we know the homogeneous function for Y. Okay, and now we can call this part your T star. You will have exponential, so T transpose C, expectation, exponential, T star, transpose, Y. Okay, and this is also the definition of homogeneous function, right? The second term here. And that is the homogeneous function for random variable Y. And we know what is the closed form of that homogeneous function, right? So we can plug in again. So let's plug in the result that we derived earlier. So T transpose C for the constant term. Now plug in the homogeneous function that we derived. So the one that we derive is this one. So now I'm going to bring this one into my solution. Okay, so this one, the one that we derived earlier, I'm going to reuse it again. Multiply by E, T star multiplied by mu plus 1/2 T star transpose sigma multiplied by T star. Okay, any question up to this point? Any question regarding any of the details here? Yes?
Is A a symmetric matrix?
It doesn't need to be. It can be matrix, it can be symmetric, but here I'm just letting m not equal to n. And might not, yeah, and it can be anything, symmetric or not symmetric. Oh, sorry, you were saying symmetric.
Yeah, I was wondering if A is a symmetric matrix.
Oh no, in this case it's definitely no, because it's not even square. So symmetric is mainly for the square matrix.
I see, but like you group A and T together with as a transpose in the parentheses.
Okay, then let's check the dimension. The thing, if that is the good question. You need to, okay, so let me double check. You were saying you need to add a transpose here,
Oh yeah.
right? Yeah.
Because when you put A and T together, I was assuming that you have the T transpose, but also you take the transpose A.
It's not symmetric, so it will have to add a transpose here. Yes, yeah, I think, yeah, you are correct. It's not symmetric, so that means I'm missing a transpose here. I need to add a transpose here.
Oh,
Okay, yeah. So let me just commenting on what I mentioned here. So T transpose multiplied by AY. This is 1 by n after transpose. This is m by n, this is n by 1. Am I missing something? Why the dimension is not matching?
What's the definition of T star?
That's here's before T star. Okay, I see. Okay, so let's be precise from the beginning. X is m by 1, so that is saying t is also m by 1. Does that make sense? So in here, the dimension is correct. So this is 1 by m, so no, not 1 by n. Okay. So this is still a scalar. Back to your question, when I'm grouping A and T together, I need to introduce A transpose T. So A is m by n, A transpose is n by m, T is m by 1, so dimension matching. So like you said earlier, I didn't write down the transpose here. I'm missing a transpose here. But after I added a transpose here, the dimension matching. And also back to your question is that the A is not symmetric. So you need to add a transpose, which I missed earlier. Yeah, so A is not symmetric. Yeah. So what I missed earlier is that I'm missing a transpose here. Okay, yeah. So for the multivariate case, it's always a good habit to write down the dimension for checking. Okay. So you will always have a correct A transpose T that. A transpose T. And I'm going to call T star my A transpose T. Yeah, so earlier I was missing a transpose because A is not symmetric, so you need to add a transpose operation there. Yeah. And after adding a transpose operation, you see n by m, n by 1, you have n by 1. Yeah. So T star, the dimension for T star is n by 1. The T is m by 1. Okay. Yeah. Thanks. Any question or comments regarding any of the dimensions and also any operations here? So also as a to check, so your y is still n by 1 and your T star is 1 by n. Yeah. But T is m by 1. Yeah. So after you make the transformation, it's still going, so it's still matching. And now I'm borrowing the moment generating function that we, so this is the, oh, is it, okay, so let me just finish in, okay, so it's time, so let me just write down the answer. Exponential T transpose C exp of, so T star is a AT transpose multiplied by mu plus 1/2 what is my T star? T star is A transpose T transpose sigma and then A transpose T. Okay, so now what I'm doing here is just I'm plug in T star. Okay. And then now I'm just expanding the terms here. So the constant stay the same, multiplied by exponential of T transpose A multiplied by mu. So now I can group A mu together. I think A mu you don't need the transformation. A is m by n, mu is n by 1, so m by n by 1, so m by 1. Okay, so A mu stay the same, you don't need the transpose. Plus 1/2 T transpose. So A transpose become A itself. So transpose and transpose back. So there's no more A transpose. So A multiplied by sigma A transpose T. And now I'm going to group these two together. EXP T transpose A mu plus C. So I'm grouping this C and this A mu together, plus 1/2 T transpose A sigma A transpose T. So this is the moment generating function for random variable x. So let me put it on the left hand side. This is the moment generating function for random variable x. And then by the uniqueness theorems, this is saying that x, which is ay plus c, following a normal with dimension m. Okay, so we started with dimension n, and here we answer with a normal random variable with dimension m. This is m by 1, with the mu, the mean vector, a mu plus c. Variance a sigma a transpose. Okay, so the conclusion here is that a linear transformation of a normal random variable is also a normal distribution. That's the first conclusion. You scale the variables by a and shift by c. The effect is also scaling the mean and shifting the mean. But the shifting a constant does not change the variance, but it will square the scaling effect on the sigma. So you have a sigma a transpose, but the shifting term only going to shifting on the mean. Okay, so that is the conclusion here. A linear transformation of a normal random variable is another normal random variable. That's the first part. Scaling and shifting have their corresponding effects on its mean and the sigma matrix. Okay, we will comment more about this next time. And thank you so much for staying over time.